China is the world's largest EV market, with over 5.5 million sold as of March 2021. This is a good thing in many ways. China has the most cars in the world, and these are replacing harmful greenhouse gases. But these things have their own sustainability concerns. There have been the concerns about environmental damage resulting from the extraction of elements like lithium and cobalt. But another concern has to do with the coming problem of waste. China is starting to experience the leading edge of this problem. In 2020, 200,000 tons of batteries were decommissioned, and the figure is anticipated to rise to 780,000 tons by 2025. In this video, I want to look at China's looming EV battery waste problem and what the world's biggest EV market is doing about it. But first, I want to talk for a few moments about the Asianometry Patreon. If you like what this channel does, you can support the work by joining the early access tier. Members get to see new videos before they are released to the public, like this one. There is also a general support tier too, and signing up for that would be amazing. So head on over to the Patreon page and take a look. I deeply appreciate anything you'd be able to sign up for. Thank you, and on with the show. Almost all of China's electric vehicles are powered by lithium-ion batteries. Their lightweight, high energy density, and long cycle life make them the first choice for electric-powered cars. Batteries have three major components: an anode, a cathode, and an electrolyte. Of these, the cathode is the most expensive and significant. We largely distinguish between these batteries based on their cathodes. Not to dive too deeply into this, but most of China's EV batteries have cathodes made of either lithium nickel manganese cobalt oxides, hereby referred to as NMCs for my own sanity, or lithium iron phosphates. The cathode composition affects the recycling process, so we will need to come back later on this. These batteries are retired when their capacity reaches about 80%, corresponding to a service life of about 8 to 10 years. This is, of course, dependent on certain factors like charging frequency, driving habits, and road conditions. Tesla, in case you're wondering, sets their threshold at 50%, not 80%. Thought you'd like to know. With the first major wave of EVs hitting the road sometime in 2010 to 2011, the infrastructure for collecting and processing these batteries would need to soon be ready by the end of the decade. That was the challenge and timeline that the Chinese government had to deal with. After the Beijing Olympics, the Chinese government began promoting the manufacture and use of EVs to the general public. At this time, the only regulations they put out dealt with industry safety standards, since many battery components are quite toxic. The early 2010s saw a growing uptake of the electric vehicle, and with that, the equally fast-growing need for a way to deal with their wastes. In 2012, the government released a policy guidance for the overall EV industry. In it, for the first time, the guidance stressed the need for, among other things, a working EV battery recycling system. In 2016, several ministries joined together to establish a unified direction for the EV battery waste problem. EV manufacturers would be responsible for recovering their cars' batteries. They must establish after-sale service networks of their own or entrust a third party to collect waste EV batteries. The Chinese government has a tendency to first declare a policy guidance or direction before setting out more specific rules later on. The 2016 declaration effectively signaled to the EV companies to expect more on this in the coming years. As such, in 2018, the policy framework follow-up came out, briskly titled The Interim Measures for the Management of Recycling and Utilization of Power Batteries of New Energy Vehicles. New energy vehicles meaning EVs and also hybrids. The enforcement body would be the Ministry of Industry and Information Technology, or MIIT. As promised back in 2016, the framework largely places the onus on private entities like the EV and EV battery makers to deal with this problem. The government will oversee some technical aspects of the endeavor, but they are not going to do it themselves. This framework is built on top of a general governance policy that the Chinese adopted called Extended Producer Responsibility, or EPR. The spiritual concept is to shift responsibility upstream from the local and provincial governments to the producers themselves. The Chinese government adopted EPR, which I believe came out of Western academia, in the early 2000s. as a response to EU directives regarding a growing e-waste problem. And it makes intuitive sense. If the government is always the one cleaning up all this e-waste, the companies making that e-waste will never be incentivized to make their stuff easier to recycle. Thus, in the spirit of EPR, all the EV battery makers have to design batteries that are easy to disassemble and provide technical end-of-life details to their customers, the EV makers. And the EV makers in turn have to either set up or run their own battery collection and recycling networks or outsource them to a third party. The government will help establish national standards to streamline the process. The framework seems pretty nice on the surface, but there are some very clear drawbacks. We will discuss those later. Now that we know the history and policy, we can next dive into a few technical details about EV battery recycling. Decommissioned batteries enter the system through two channels, from cars undergoing a battery replacement and from cars at the end of their life. For the latter, the battery is still inside the car and is removed as part of the end-of-life dismantling process. This remains a very manual process, especially in China. After that is a step called pre-treatment. The battery cells have to be pulled out of the pack and opened, which is a challenge since there is no standard battery pack design. Thus, it has to be done by hand using specialized tools. Once the battery is removed, what happens next depends on the type of lithium-ion battery inside the car. Let us start with the NMC battery, the most common in China. For NMC batteries, recyclers want to recover the cathode's active materials. A 2019 economic analysis estimates that despite making up only 4% of the battery's weight, they make up over 60% of the battery's overall salvage value. NMC recycling technologies are relatively mature. Sony pioneered it in 1999. There are two major technological methods, pyrometallurgical and hydrometallurgical. Let us start with pyrometallurgical. Pyro means fire. The battery is melted into an alloy of iron, copper, cobalt, and nickel. The good stuff is then retrieved using hydrometallurgical methods. Pyro methods burn off electrolytes, plastics, and lithium salts, so not everything can be recovered. It releases toxic gases that need to be processed, and it is quite energy intensive, but it has been widely adopted by the industry. Hydrometallurgical methods use an aqueous solvent to separate the desired materials, like cobalt, from the compound. The most commonly used solvents are sulfuric acid and hydrogen peroxide, but there are many others too. Neither of these methods are ideal, and further work is needed to address their technical shortcomings. Lithium iron phosphate batteries make up about 30% of the Chinese EV market as of 2019. These batteries' energy densities are not as high as their NMC counterparts, but they are free of elements like nickel and cobalt. They are also probably safer. China is also the world leader in the science and commercialization of lithium iron phosphate battery technologies. Chinese company Contemporary Amperex Technology, or CATL, is one of the manufacturing leaders in this area. It should make sense that the country's industry be able to recycle these cells too. That being said, recycling these things has turned out to be more technically difficult than at first anticipated. This is in part due to them having a more varied mix of materials, which necessitates additional expensive pre-treatment work. And then economically, lithium iron phosphate batteries do not have the same valuable metals like the NMC batteries do. No nickel, copper, or cobalt. And it has led to a dearth of investment in the niche. There are some promising hydrometallurgical experiments that have been able to leach out up to 85% of the lithium in the form of lithium carbonate. Speculation is that it would cost about $650 to process a ton of spent lithium iron phosphate batteries. That includes energy and material cost, not counting the cost of building the factory. The potential recovery and resale of lithium could help make recycling more economically feasible to do. But the jury is still out on this, as these methods have yet to be implemented at commercial scale. The 2018 framework lays out a lot, but it does leave a few things to be desired. As we all know in life, not everything gets tied up in a neat little bow. There are a few missing holes here. So let us talk a little bit about some of the policy questions still up in the air. The headlining statistical goal at release were raw material recovery rates. 98% of nickel, cobalt, manganese, 85% for lithium itself, and 97% for rare earth materials. Theoretically, this is all possible. For instance, I just talked about recovering 85% or more of the lithium from lithium iron phosphate batteries. I also mentioned that it will be hard to achieve this theoretical maximum due to real-world inefficiencies and differences on the ground. Remember, there are a lot of ways that battery cells can be made, packed, sold, and used. There is nowhere near the standardization that we see with cylindrical batteries sold in your 7-Eleven. The policy framework is missing concrete subsidies and national support for making this come to real life. Another big concern is economic. The policy framework does not allocate money to incentivize the collection of used batteries. There are a few buyback pilot programs run by the municipalities, but nothing at a national level. This could change, perhaps with a levy or a tax, but right now the private sector players have to fund it themselves. This is an issue because there is little economic incentive for these big EV makers to collect and recycle their batteries. From 2008 to 2015, the cost of manufacturing an EV battery declined from $1,000 per kilowatt hour to $268. That trend is expected to continue over the next few years. The drop in costs made EVs more accessible than ever, but at the same time, they have also lowered the incentive to collect and recycle these batteries. And since these batteries are all so different from each other, it is hard to scale up the collection, pre-treatment, and recycling processes. So the whole venture turns out to be a cost drain on their manufacturers who already work on pretty tight margins to begin with. Regardless, the EV makers by law are first in line to handle and recycle their old spent batteries. And despite the economic unattractiveness of the whole venture, they have been diligent in partnering with large companies to set up official channels to recycle a battery. A few large recycling companies have sprouted up. Examples include Taisen Recycling, Zhejiang Huayou Cobalt, Jiangxi Ganfang Lithium, Hunan Brunp, and market leader GEM. But despite the existence of these licensed large companies, the majority of the Chinese recycling sector is made up of small, unlicensed workshops. These informal shops do not have the proper tools or training. They basically go to town on these batteries for their cathode materials, reselling them to the highest bidder and dumping the rest. Obviously, this is a massive safety and environmental risk. As a result of this skirting of rules and regulations, these chop shops can pay EV owners more for their batteries, and, as such, are preferred over quote-unquote official channels. Thus, the lithium-ion recycling rate in China remains quite low. In 2015, it was about 2%. It has since grown to 10% in 2019. It beats a sharp stick in the eye, but this is still far from ideal. And the 2018 framework does not set a target on battery collection rates, a curious omission. China has been struggling with this problem on another battery front, the venerable lead-acid battery. This 150-year-old technology is very commonly used. In China, they provide the start power for their automobiles and are still very popular for e-bikes. This is despite recent regulations to encourage replacing them with lithium-ion. Anyway, Chinese recycling of the lead-acid battery falls far short of expectations and benchmarks. In 2017, less than 30% of the 3.3 million tons of lead-acid battery waste generated in China is recycled. The reasons for this low recycling percentage are very similar to the lithium-ion case. Informal chop shops skirt the rules and regulations, and thus can afford to pay a whole lot more for consumers' batteries. The Romans have made it clear that lead is not exactly the most environmentally friendly substance out there. China has experienced multiple major lead poisoning incidents in recent years as a result of this improper handling. Thus, the government has recently pledged to crack down on these informal shops, of which it is estimated that there are over 200 across the country. The goal is to try and hit a 40% recycling percentage in 2020 and 70% in 2025. Considering that the lead-acid battery recycling percentage in America has been at 99% since at least 2014, it should not be that difficult. Considering the technical and economic difficulties associated with recycling EV batteries, the industry has thought about ways to make more use of these things before sending them to their grave. The highest potential option would be to reuse them in power grid projects. These batteries still have 80% capacity after all, and can still go for many years before finally conking out for good. The United States leads the way here, having experimented with used car batteries for stationary energy storage projects since 2002. But China has done some interesting demonstration projects. One of the longest operating ones is the Dangbei Wind and Solar Energy Project in the Hebei province. The $1.3 billion project springs from a joint effort from Chinese state-owned enterprise State Grid and EV battery maker BYD. It demonstrated the feasibility of using Second Life EV batteries to support and manage a power grid. More EV battery recycling projects have come up in recent years in Beijing, Jiangsu, Zhejiang, and Shenzhen. The government is putting a lot of focus on this, but I think ultimately it more forestalls the recycling problem than solves it, because the inevitable end of every battery is either recycling or the landfill. The Chinese government has done an admirable job in encouraging the creation of this thriving EV ecosystem. The country is the unquestioned leader in certain aspects of battery technology, and several EV giants are based there. They have a chance to really bend the curve in automobile emissions. So in a way, this recycling issue is a nice problem to have. It is an indication of China's success. But a problem is still a problem, and the industry has been dragging its feet in establishing the proper recycling networks, regulations, and technologies. The Chinese government can look to United States policy for some guidance in incentivizing and enabling proper consumer recycling habits. And subsidies need to be doled out to enterprises in the pre-treatment and recycling technology industries, not just in manufacturing. Otherwise, the energy usage and environmental damage associated with these battery disposals will outweigh whatever benefit we get from switching over to EV. Alright, that's it for tonight. Thanks for watching. If you want more content, you can like and subscribe to the channel. The feed will show you a bunch more new videos like this one to watch. Remember to hit up the email newsletter, sign up. If you want to send me an email, drop me a line at john@asianometry.com. I love reading your emails. Introduce yourself, suggest a topic, or more. Until next time, I'll see you guys later.